Where we were is we were at a point where we were discussing some of the key parameters here. There's a couple things that we will cover still. I'll try and keep an eye on the last few, trying to jump in. But what we were covering is there are smaller substitutional impurities, and this can do a number of different things. One of the biggest factors for this is going to be how you have substitutional impurities that are smaller or larger, and in both cases what they do is they redirect the stress and prevent the strain from being able to move through the material as easily. So we have a stress at A and B. Those are stresses that are being generated that resist the motion of the dislocation through the material at both of those points. Same thing at C and D for the larger side of the impurity. So you have above, where you have the inserted half plane of atoms, you have compression because everything is being squeezed into the same space, so that should make sense. Tension is where it's pulling apart at the bottom side, and it's being pulled so strenuously that it becomes under tension. And so especially right at the level just below where the inserted half plane is, right at that boundary. So this is where we were. One of the things that we're trying to do by solid solutions and alloying is we are trying to strengthen the materials themselves. So these small impurities tend to concentrate at these regions of impurities, and we have to move through the material. So I wanted to give you guys an example of what this looks like. Let me see if I can find my favorite example. There's two of them that I want to give as an example, and one of them, these are a couple from couple that you should recognize, but let's go ahead and bring this up. Multiple reasons why this is immediately relevant, because this is going to start talking about alloying and strengthening by select impurities in order to make this in order to make the whole thing work a little bit better. But this is going to put a direct practical application to it, which I think you guys will appreciate.
Quiz. If you were able to look back on the present from deep in the future, what age would you say we're living in?
Is this a trick question? I mean, I want to say information age, but it seems too obvious. Can I say more than one age?
Yeah, I think it is safe to say that we are living in more than one age. From the beginning of humanity, we've seen prevailing technologies marked with milestones: the Stone Age, the Bronze Age, the Iron Age, all occurring many thousands of years ago. Man's mastery of these materials has defined us, but by that metric, the last couple of hundred years have seen a flurry of ages. The steam age, the industrial age, the atomic age, the television age, the space age, to name but a few. But those are not the answers I was looking for.
Is that a clue?
Yes, it is. I think that this age could be classified as the Glass Age.
That's not what I was thinking.
I know.
So how are we in the Glass Age?
Well, let me put it to you this way. Can you imagine a world without glass? Now, I don't want a cheeky answer. I want you to really think about it.
Okay, no. I can't imagine the world without glass.
Exactly. Glass is really quite extraordinary. Without it, many of our major accomplishments would never have happened. Glass has a deep and complex history, and as a material, it has properties and characteristics that we are only just beginning to understand. We look right through it and think of it one-dimensionally. Most of us think of glass as a fragile, brittle thing that, if not handled correctly, will break in a spectacular fashion.
So you're going to break that to make a point?
Indeed.
Can I help?
Yes, you can. And it's true, our everyday common variety of glass is brittle, but it doesn't have to be that way. Glass has already altered our lives and is behaving in ways that is totally unexpected.
Got it.
Let's start with a history of glass.
I think I can handle that. Glass as we know it is most commonly made of silica, the primary ingredient of beach sand. Mix silica with a couple of other key ingredients, heat it all up till it melts, and bang, you got glass. Humans have been making glass since ancient times, starting with beads, vessels, and ceremonial accoutrements. Glass-making techniques spread out from Mesopotamia, culture to culture, changing in incremental ways for much of the last 4,500 years or so. The Romans even had glass windows on their important buildings as early as the 1st century AD. Glassblowing was discovered around that time, and soon inexpensive and ubiquitous glass became one of the hallmarks of the Roman Empire. But no period has seen such growth in the development of glass technologies as in the last 150 years. We've been able to unlock the secrets of glass in ways that would have seemed like magic to our forebears.
Nice.
Thanks.
So tell me what's so special about the last 150 years?
Well, several things. In that period, technology evolved at an exponential rate. With that came tools and processes that enabled advancement across all material sciences. The leader in glass material science was, and still is, an upstate New York glass company that started out in the mid-1800s, Corning Incorporated. One of their first products was a toughened glass lens for railroad signal lanterns that offered 2 radical improvements over any other lens of that time. It could be produced in a consistent color, and more importantly, it didn't break when rain hit the hot glass. This helped save lives by bringing down the number of train wrecks, but it also set a course for 160 years of innovation in glass. Of course, everybody knows about Corningware and Pyrex products too. Those innovations came from Corning during the early part of the last century.
You know, I have tons of this in my kitchen.
But Corning no longer makes kitchenware. They've innovated way beyond that. Let's take a look. We'll start with this.
Ah, optical fiber.
Right, optical fiber. This does 2 things, both astonishing. The first one is this.
That right there is pure glass. A glass strand inside the cable, tightly wound around a pencil and yet not breaking. When you stop and think about it, that is a mind bender. Okay, what's the second thing?
Well, it's the way the light moves through the glass. When the glass is bent this way, you'd expect light to leak out and get weaker and corrupt the data that it carries. But that's not happening. Nearly all the light entering this optical fiber is coming out the other end.
So it has a low attenuation?
Yeah, exactly. Very low. In the late 1960s, Corning figured out how to limit the attenuation or loss of light as it travels through fiber, even when that fiber is bent.
Nice.
This discovery led to the practical use of fiber as a medium for voice and data communications over great distances, ushering in an era of low-cost, high-bandwidth communications and ultimately the internet as we know it.
Wow, so just how much data can these optical fibers carry?
This video playing back right here is sucking in data at around 20 gigabits per second.
It's a lot of data.
Yeah, this is ultra high definition raw video, but even in this case, the optical fiber is not anywhere near capacity. The bottlenecks are here and here, not here. The practical limit of data transport over optical fiber keeps increasing. Using today's technology, it's possible to transport more than 1 million gigabits per second, about a petabit. That'd be like downloading 17,000 high-definition movies from Netflix in a single second.
That's amazing. Okay, tell me about this stuff.
Well, obviously it's an optical fiber as well, but instead of sending light through one end and out the other, it emits light throughout its entire length.
Cool. What's it good for?
I have no idea. Okay, so I was able to seriously bend a strand of glass. Didn't break. But what do you think's going to happen when I try to bend a pane of glass? Rhetorical question. Check this out.
That doesn't look like it went very well.
Well, that was soda lime glass, the kind of normal stuff we see around us every day. But watch what happens next. This is glass too. It's called willow glass, also made by Corning. And it's flexible.
No way! I cannot believe that is glass.
Well, it is. There's no trickery here. This is glass, but it's as flexible as paper.
So what kind of applications does that have?
Well, that's where it gets really cool. Check this out.
All right, it's looks like a piece of stainless steel. And what is this? Willow glass bonded to one side as a scratch-resistant coating?
Yep.
Okay, but tell me this, how is the willow glass anywhere near as durable as stainless?
Well, that's a good question. Watch this.
That is amazing! I cannot believe that the blade did not shatter the glass.
It didn't. And that's just half the story.
All right, so what are we doing?
Give me that.
Okay.
Take this.
This is heavy, man. What do you want me to do with it?
I want you to drop that right on that piece of stainless steel with the willow glass on it.
Seriously.
Let's see what happens.
Here we go. 3, 2, 1. No way!
It dented it, but it didn't break the glass.
That is insane.
And you can attach this to just about any solid surface.
Bendy, flexible, durable glass. Impressive. And characteristics you wouldn't normally associate with glass, right?
Right. I like this new glass age we're in.
So where we are in terms of these materials on the whole, you can see that this was a production from exactly 10 years ago. And there are already now, we're on to version 8 or 9, if you go by Samsung's nomenclature, of the folding glass devices that are using this kind of technology. Crystals, as we've learned, do not like to be folded because of what happens with these materials. But there is some metric by which, going back to this concept, there is some metric by which we have these small impurities and large impurities, and depending on what we're trying to do for that particular application, we can tune the overall properties of these materials to behave in unusual or unexpected ways. So there's a lot of things that happen, but there's another piece to this puzzle, and this is where we get into this. So I want to show a demonstration of that side of this as well. These dislocations have a difficult time passing by where the impurities are because of the compressive strain that is built into the system at that point. So it's partially a cancellation of that dislocation motion through the material. So it can run through the material along a diagonal until it hits a fault, and then it can't as easily run through these dislocations. So these dislocations reduce the reduced mobility of those dislocations increases the strength of the glass. And this is why something like that willow glass is able to absorb the impact without shattering in the way that soda lime glass does. There's a different mobility of the material, and that's what allows this flexibility. Now, it is cycle limited, so you'll see a lot of instances where those have been broken. Similarly, these large impurities tend to concentrate dislocation, or tend to make it difficult for dislocations to propagate, because it provides compressive strain again in this same area. So there are regions of tensile strain around where these are, and that becomes much more difficult. So they show you some examples in the visualizer, but this compared to what I'm going to show you as an alternate example is going to be helpful in making sense of this example for copper, even though it's in glass and it's a different material, because the fundamentals are the fundamentals the world around. So I'm going to go to the second one, and we're going to share that, because this will deal directly with the impurities and what the compressive strength of the glass actually is and what it does.
Let's switch gears. Your smartphone. You hold it in your hand, you put it to your ear, you keep it in your pocket or your purse. It's a great everyday use of glass that you might not think about.
Till it breaks.
Until it breaks. I myself have shattered over a dozen of these, but you might have noticed over the years that the display on your phone has been getting harder to break. Let's go back a few years. If you'd done that to your standard 2008 phone, that's what would have happened.
Not pretty.
No, and that could easily happen just by keeping your keys and your phone in the same pocket. And if you then dropped that phone, well, the probability of the phone breaking was high.
How high?
Very high. Let me show you.
Aren't you going to drop the phone?
Well, sort of. Instead of dropping the phone, I'm going to drop something on the phone, this steel ball.
For consistency's sake.
Exactly. In this way, my phone drops exactly the same way every single time. Here we go. 3, 2, 1. Oh.
I've seen you do that so many times in real life.
Me too. But that was then. This is now, thanks to Corning, we have Gorilla Glass.
I'm pretty sure that's what I've got on my phone.
And it's on this phone as well. I'm about to do the same test a second time. Check this out.
No scratch.
Not at all. Now, same drop test. Ready?
Yeah.
3, 2, 1.
Wow. What a difference a few years can make.
Actually, Corning came up with this method for strengthening glass long ago. Gorilla Glass evolved from that process and today is found on all the best small devices like this. It's beginning to find its way onto larger format displays too. Now, it's not unbreakable. If you set out to break it, you will. But as Corning figures out ways to unlock more secrets of glass, it will continue to get more resilient. It may even get to a state where devices such as these simply don't break anymore. Oh, and by the way, Corning has just come out with a new and improved version of Gorilla Glass.
Really?
Yeah. Let's go deeper. Watch this.
Hot stuff.
Yeah, this hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. There we go, and I'm going to drop it in cold water. It's called a Prince Rupert drop.
Who's Prince Rupert?
Some Bavarian from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the backside of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Whoa! That was even cooler than I thought it would be. That is what happens when you release the stress in compressive strength glass. The whole thing shatters.
Spectacularly.
Yes, well, at least in that example it was. That's because the stress was so great between the outer compressive layer and the inner tension layer.
That when released, it was a catastrophic result.
This is Gorilla Glass. It has been refined over time, but like all Gorilla Glass variants that came before it, it is compressive strength glass. But it's not made in the same way as we just demonstrated, the rapid cooling method. No, instead, Corning uses an ion exchange process. To break it down simply, the surface ion particles that naturally form during the manufacture are replaced with larger ion particles. Once exchanged, the larger ion particles create the same sort of inward pressure that we see on the Prince Rupert drop. And with this method, they are able to control and manage the resulting tension.
I think what you're saying with this process is that they're able to tune strength in the glass by dialing in the right balance between compression and tension?
Yeah, that's a great way of saying it. That, and also by adding in a few other tricks that change the molecular structure of the glass. Corning is steadily moving forward towards the Holy Grail.
Thin, unbreakable glass for our mobile devices?
Well, maybe not unbreakable, but yes, thin and very tough. And by the way, the applications for this tough glass go well beyond mobile devices. Let's go over this way. Behold, the common automobile windshield made from regular soda lime glass. It's quite strong because it's very thick and it's laminated, which means it's two pieces of glass bonded together using resin in the middle. And the resin does two things. It gives it added strength and it holds the glass together on impact. You've probably seen broken windshields before. Lots of crazy cracked glass, but still mostly held together in the shape of a windshield.
Like this. That's pretty cool.
Yes, it is. Windshields have been made of laminated glass for the last 100 years, and they've served us well. But there is a big drawback.
I think I know what you're going to say. It's heavy.
Yes, very heavy. And as we strive for more energy-efficient cars and trucks, the weight of all that glass can be a bit of a problem.
I have a feeling you're about to show an alternative.
Yes. Take a look at this. Now, this is also a laminate windshield, but it's not one you'd find in production. It's experimental, which is great because we're going to experiment with it. It has regular soda lime glass on its outside surface and resin in the center like the other one, but this windshield has Gorilla Glass on the inside surface.
Sweet. It looks thinner.
Yes, it is. And a lot lighter, too. In fact, just by changing the one laminate, the overall weight is reduced by about a third. In a car, that adds up fast.
Thinner, lighter, and let me guess, it's just as strong as windshield A.
Well, maybe. Let's find out.
Oh, goody.
Okay, wait. No. You don't need the sledgehammer for this one. Put that down. Instead, you're going to shoot this windshield with an air cannon.
Cool.
No, don't get too excited. We're going to have to mount this, tie it down so it doesn't wobble, and we're going to simulate a pebble hitting this windshield at a super high speed.
Good enough for me. When do I start shooting?
Well, before we shoot the Gorilla Glass laminate, let's shoot the regular soda lime laminate, windshield A. This way. All right, here we go. Perfect. You want to do the honors?
Sure.
I'll count it in. 3, 2, 1, go.
Whoa.
That was a lot of damage.
Can we see that in slow motion?
The ball bearing hits the windshield at around 120 miles per hour. This could be a stone flicked up by another car. It penetrates the exterior glass, it stretches the resin, it's slowed down a bit, but it still has momentum to break the interior glass layer, causing small fragments of glass to spray out through the interior of the car.
Not good.
So let's try windshield B. The Gorilla Glass didn't appear to break. The foil is intact.
Let's see it in slow-mo.
The ball bearing hits the windshield at around 120 miles per hour, just as before. It goes through the front layer of soda lime glass, stretches the resin, but doesn't have enough energy to break the Gorilla Glass. It's not bulletproof. I'm pretty sure if we turned up the velocity, we'd breach the Gorilla Layer too. But in this test, and all things being equal, it performed a lot better than the thicker, heavier soda lime laminate windshield. That's impressive. What we're seeing here is compressive strength at its finest moment.
Okay, so it's lighter, thinner, and stronger. That's pretty good.
Yes, it is.
Can I get this on my car?
Not today, but soon, I hope. Come on, though, after living through the Iron Age and the Bronze Age, you can wait a little longer. Actually, when you think about it, the application for this goes way beyond the car, doesn't it? Ah, yes. Feels good to be in the Glass Age. Come on.
Don't touch me.
Sorry.
So there's a lot of useful applications of this principle, and this is why it's important to have a general understanding of what these substitutions can do in terms of the material strength. So we understand that the idea of changing what is dissolved in the solid state, i.e. the solid solution, can create a stronger material. This is an example of a graph that shows you differences in tensile strength as well as yield strength based on the nickel concentration. So from 0% all the way up to 50% nickel added into copper. So the more nickel that's added in, the greater the tensile strength and also the greater the yield strength. In fact, almost 3 times the yield strength at 50% nickel. This also gets into the importance of alloying materials, because the way that these work is having multiple different kinds of atoms working together in these crystalline lattices to add compression and tension in the right balances, because that tunes the parameters of the material to get to the end state for where you want it. So they give an empirical relation here, which is roughly based on the measured data. The yield strength is proportional to the square root of the concentration of copper. It's a thing that makes sense experimentally because or the concentration of the nickel in the copper, rather. So the change in concentration, that value, the square root of it, is proportional to the yield strength. So the higher the concentration, the higher the yield strength. But there's a definite knee to the curve where after you've doubled the strength, you have to go a lot farther in terms of alloying to get a little bit more out of it. So you start out low as you add the alloy, and it's both the tensile strength and the yield strength that's more than doubled here. In the case of the tensile strength, it's doubled, but in the case of the yield strength, it's almost tripled. So the alloy makes a huge difference. So this is part of the reason why you need to have some sort of an idea, even though it's copper, depending on who made it and what the nickel concentration is. It might be twice as strong, or it might be half as strong, depending on how it's alloyed. So very often you're going to have some degree of alloy, but if you don't have good control over your manufacturers and good quality control in your supply line for what you're building, then you don't know whether or not the copper will be of the correct type and alloy. So another thing that's a strategy for strengthening is precipitation. Precipitation hardening is a little challenging. So these are the hard precipitates are difficult to shear. The idea here, and this is actually a pretty reasonable graph. The idea is you're adding shear across a plane, and then if you have a precipitate, especially if it's if the plane is bisecting that precipitate, you have to have a very large shear to be able to break through that precipitate. So something like ceramics in metals, a silicon carbide in iron or aluminum is a good example of a precipitate that is very, very hard, and in order to shear it, you have to work a lot harder. So this is part of the reason why tooling has silicon carbide added in to the iron, for instance, to make cutting tools. Is that level of precipitate means that it's very, very hard as the cutting edge is shearing other materials. It has all of these precipitates to fight against its own atoms being sheared along dislocation and slip systems. Whereas the material that it's machining typically is going to be softer and not have that kind of thing happening. So there's in a top view, there's a part of a slip plane here that's given as an example. The dislocation can move through the material, but the precipitate stops this from actually happening. So things are trying to shear on the side here. Things are trying to shear these materials apart. From the top view, you're seeing that the precipitates almost pin these dislocations, so they can't continue to run through the system. They get stuck at the precipitates, and that slows the advance. So even though the precipitates can still sort of move, it creates some issues. So the yield strength or the yield stress is proportional to 1 over S, the distance between these precipitates. So the approximate spacing of the precipitates. So this allows for a material, by careful alloying, to be able to behave in a way like a much, much, much harder material while being less expensive. So this is part of the reason why we use iron with all of these different alloys for different kinds of tooling steel, because making things out of all more exotic materials like Inconel is more expensive and harder on tooling and all of those sorts of things. So we're able to get a fundamentally weaker material to behave as a significantly stronger material by careful control over the processes that we run them through. And that's a big part of this. An example of that is the Boeing 767, which is now probably old enough that most of you have not actually ever been on a 767, and it's entirely possible that you might not have actually seen one in person. So this is getting to be kind of an aged example, sort of like the photo itself. But the idea is the internal wing structure is precipitation hardened, so it's aluminum, but in order to make it stronger, they have all these little precipitates in the material in order to keep dislocations from being able to run. So the reason why these why these can take all of these repeated stresses and not have fatigue build up in a way that is detrimental to the airplane, right? You think about how big of a problem it would be if every 10th time an airplane went through severe turbulence, one of the wings just slightly came off or something. This would be very bad. So they have to have materials that are stronger. And so when people say, you know, oh, it's aircraft grade aluminum, that probably just means 6061, which is kind of the everything aluminum. It's also aluminum camping cookware aluminum. Like, yeah, okay. So they're not actually using this kind of precipitate hardened aluminum like is actually used in the wing structure. So why did they use those on the wing structures? Because in an airplane, wings are sort of important. Another example that they give is cold working. And this is one of the ones that you guys are going to do in a lab. You've seen kind of a preview of what it looks like in order to make this work. And the idea is deforming at generally room temperature for most metals. So there's operations that happen that reduce the cross-sectional area typically by applying a force. So die stamping, drawing through a die so that you have an initial area, you have a drawn area, so an AD, and you have tensile forces being applied. So you elongate the grains and stress them. That's an example. Rolling or cold rolling is exceptionally common material. So you saw the examples of sheet steel being rolled up. And that's always a big deal. So smashing it and applying a force between a couple of rollers so that you have an initial area and you have a die drawn area. And then you have extrusion, which has a ram, a billet, you have some sort of a die and a die holder that forces the metal through. That's something that is done with steel, but that's not as common. It's a lot more common to have extruded aluminum. So think about something like aluminum square channel or the material that are commonly used for frames for various kinds of industrial equipment as well as 3D printers because of its low expense. So they have a die that's a special shape and they push the aluminum through that special shaped die in order to get the extrusion formed. So a lot of aluminum angle and all sorts of things like that are made using this exact same format. So it really makes a big, big, big difference. So the dislocation structures change during cold working, and this is an example of a dislocation structure in titanium after cold working has been done. So the dislocations entangle with one another, and that's what they're trying to show here. So all of these dark lines are dislocations in the material, and as cold working happens, all of those dislocations get tangled up in kind of almost a web, and that means that the dislocations kind of get caught on each other in a way, and so they can't go anywhere. So cold working does make the material harder, but it's specifically because of what is happening with these dislocations and them getting entangled and not being able to run farther through the material. So let's look at some examples. I think I've found a couple really good examples of steel being run through die stamping. There's a couple others. Let me see. Yeah. There's also examples. Yeah. There's a couple that are actually making the dies, but there's also some deep drawing materials. There we go. By an actual company that builds the equipment, and that's a much better representation than some sort of hokey YouTube short. So what they're doing there, without the rock and roll music of sorts dubbed over Chinese manufacturing processes, which is humorous on many levels. The progressive die stamping especially is one of the things that we're talking about, because sheet metal bending is pretty straightforward, where you have a channel that it's forced into to reshape the material. That part's pretty straightforward. But an embossing is where you're adding logos and things of that nature into the material. The progressive stamping, this is the part where they're moving these pieces along through a process. They're punching holes in the center in order to create the part that's desired. So this is the cap for thermostat, so that thing that keeps your car from boiling over in the intense 135 million degree heat in Phoenix. This is the top hat of a thermostat, and so it's a very special piece that has to be a certain thickness, and so it's creating all of these different features by stamping it multiple different times, and then punching and literally ripping out this material that doesn't get supported by part of the die, in order to leave you with a ridge that holds on to a gasket. So each and every single feature of this, there's a a ridge on the inside of this part that's holding on to a set of prongs that is a retainer for a spring that sits in there. So all of these features you need to get in the end part. Machining it with a CNC would take many hours per unit, whereas if you've designed it well, you can do a stamping operation that within probably not even 10 minutes from a blank steel die or a blank steel sheet, it can output these kind of complex geometries with many, many, many different features, and even some of these holes that are punched in order to allow for a very metered flow of water past the unit. If it gets seized shut or some other stupid thing, there is still some small amount of flow that is allowed. Even the width of these channels is a very specific dimension for a specific purpose. So all of this goes into what regulates the temperature in your car's engine. It just happens to be something that has a lot of specific requirements that stamping can provide. So steel is a lot more useful material because steel can give you the strength at a lighter overall mass. And that's one of the keys for this. So it's important to understand kind of what the applications look like, because what they're doing is they're stressing the material out by cold working it. They're running these through this kind of stamping process. And what it does is it does the same sort of thing here by forcing it together and shrinking its overall profile. They strengthen it and then they draw it out in other parts of the forging operation, then changing the direction of where the force is applied. So it gives it compressive strength at that top hat where it's holding on to the pin that retains the spring, so that it doesn't come apart, even under thermal cycling. And that's why a material like steel is needed in the first place. So that cold working percentage is the difference between the area originally and the deformed area divided by the original area times 100%. So cold working is often changing it by a significant amount. The extrusion process, they really didn't show. I wanted to see if I could grab an example of that because it's really yeah, there's a couple examples. Often steel is going to be this is a good example of what the same material does in multiple different dies at the same time. And then we'll take a look at some aluminum extrusion and a couple other of these processes. Yeah, for H and I beam, that's a really good example, as a matter of fact. So I'm going to include that one as well. But this is the first one. We can do this one without the sound just as soon as the ads. This one is actually probably okay with it. But it's important to understand where this comes from. Each of those, given the same feed rate of material, behaves quite a bit differently, and the varying hole depth, diameter, and shape. So here would be an example where you can see the distance between the flange, and the flange is this flat part that gets caught in the clamp. There's a mirror flange on the back side. Usually there's some sort of inset. You guys will learn about that in other classes. But it's the same number 6 clamp that they're using in all circumstances. So the difference is this is a 12 and this is a 12. But this one is deeper relative to the flange compared to this one. So the material just falls out of this one because it's a powdery material that's being fed at the top. The deeper die gives it more time to compress and makes it a stronger material, which is why you see material falling out sort of immediately from the short die, and then you don't the same way from the longer die, even though the material is being fed at about the same rate. So the thicker die, the smaller the diameter, the faster the material flows through. The larger the diameter, the slower the material flows through at a given flow rate. But the difference, especially between the short and the deep die, is very significant. That's why I wanted you guys to see that one as an example. The other one, there are, this is a large. So you can see how many different operations had to be happening in order to start from a large billet, is typically what it's called, to get to an end state with a controlled diameter and a consistent size. And this one happens to have a significant lip, probably because this is going on to a large piece of machinery like a mining trommel or something of that variety, where they're going to need a lip in order to weld the interior casing to, in order to have it run and rotate in a truly round format. And there's a lot of other examples that they give of how to create much more complex pieces at a much larger scale, but not have to have a CNC the size of an industrial building. So that's a pretty wild example. The other one that I wanted you guys to see was this process, which is the hot extrusion process for steel.
I could never go on vacation.
That's sufficiently far to give us a pretty clear indication of what's actually happening. The keys there being the process has multiple steps with specific depths of rollers, and it kept moving and migrating the beam back and forth through each of the series of stepped rollers that have a deeper and deeper and deeper groove. So they're pushing more and more and more material, and then running them through some more dies that again continue to hot roll the material. So it can have a little bit of side to side distortion still, and they even that out in later processes. And this is where they cool the beams down. So they air cool the beams to get to the exact properties that they want, and they move them all in a line with all these carefully timed and synchronized parts themselves made of I-beams. So some of the final steps is truing up is what this process is doing, is fitting it through a roller one last time to true up or straighten out any kind of bends, because it will force the steel to become even along these very long lengths. Then they cut off the ends after they've finished cooling further. They cut off the ends in order to make length cuts in order to meet the customer requirements. So there's a lot of moving pieces to all of that. This just helps kind of set a little bit of the framework for why it is that we're doing these kinds of processes for the materials. So multiple different steps. Very rarely is it all going through a single step process. And all of those dislocations and things, the dislocation density changes as part of that process is done. So there are a lot of different steps, and there's heat treatments that happen along the way, or they start out with the steel at very high temperature so that they can square it up through a die, then start running it through the rollers to get a consistent thickness. That way, by the time they are done, they have cold rolled along two of the axes where the material is going to see stress. So the side to side and then top loading. So side loading and top loading are the two primary concerns, and that's why they're made in such a way as to use the worked side, the worked grains that are stretched out along the length of the material. That makes it very hard for I-beams to bend. So everything about the way that they make the I-beams, it's not just the geometry, but everything about the way that they make them and how they process them is about trying to get them all to work correctly. But you can't just extrude a final dimensioned I-beam out the end and have it be very controllable. So it's a long process to make those kinds of I-beams, and that's why structural steel, good structural steel, is not cheap and never has been. So this gives you guys at least some sort of a way to understand the context of what we're trying to do and how we're trying to control the end crystallinity of the materials in order to do the job that we need it to do. So I think we're going to pause there because I know a bunch of people have to jump and run to classes and all those wonderful things. I want to make sure that we are getting all the information that we need. But are there any questions as we go to wrap up?